Here's the most fundamental slide of all. We nickname it V&V in simulation technical talk. Verification and validation are both required in order. They're sharply distinct. First, what does the model do? Middle circle. At the right, if I'm the modeler building that model, which I've done many, many times in my 40 years of simulation work, is the model doing what I thought I told the computer to do? Verification is very much what in computer programming talk has always been called debugging. Did I build the model right? Did I build it the way I intended? That comes first. Then it's time to look to the left. You're building a model that you're going to analyze because a real-world manager, client, engineer is going to use the results of that model to guide business decision-making. The model has to be able to do that correctly. Therefore, the model must match in all its important behavior what the real system does. If you're modeling a real system that already exists and needs to be expanded or improved, or what the real system as visualized, perhaps on the back of a cocktail napkin, will do if built as designed and sketched out. That is validation. So verification, did I build the model right? Validation, did I build the right model? The right model is the one that accurately imitates the real world in all important respects and therefore is fit to guide business decisions. So verification comes first. Validation involves the client much more. Very close, frequent communication is necessary during validation. So there's the distinction, model right versus right model. And both are necessary for the model to achieve credibility. Credibility means that the decision maker, such as client management, trusts the results of the model enough to use them in guiding business decisions. If the model does not achieve credibility, it was an exercise in futility to build it in the first place. So after validation, talk with your client, make sure that the client feels comfortable with how it's working so that the model can achieve credibility. Now, some verification techniques. Simulation work is essentially programming, although with the newer software, the need to actually do what traditionally is visualized as writing code has become less and less. There is less code writing now. I didn't say none, but there's less, and more drag and drop, point and click, and so forth in modern simulation software. However, the concepts of modular programming should still be used. Those concepts include things such as build the model a little at a time, verify and validate it as you go. Whenever possible, write one set of code that can be used in multiple places or reused in projects B, C, E, and F whenever applicable. Maybe it wasn't applicable to project D, after being used, debugged, verified, and validated in project A. That reduces the likelihood of error and increases the efficiency and time to delivery of modeling efforts. So these concepts that traditionally were called structured programming carry over and are vitally important to simulation work. Every modeler should do this with every model. Let only one entity, now the entity is whatever you want, that's part of the beauty of simulation. In a warehouse model, the entity might be one incoming truckload. In a hospital emergency department, the one entity might be one patient. In an airport luggage handling control system, the entity might be one suitcase. In a restaurant model, it might be one group of 1, 2, 3, or 4 people who want to have dinner together. Let that one entity into the model, only one. Where does it go? How long does it take? Is it going to the correct places based on its properties and choices? Is it spending the correct amount of simulated time in those places? That is a fundamental part of verification. Remove all randomness. Now, you probably would not be simulating at all if your process had no randomness in it. Randomness, my goodness. At least on this planet, now I've been reading a science fiction book that says on Neptune and 2 of its satellites, there's hardly any randomness. But we have random product demand, random delivery times, random cycle times, random downtimes, random repair times. My goodness, here at the third rock from the sun, we're full of it. So the simulation model is certainly, ultimately, going to contain randomness. But early on, take the randomness out, or don't put it in just yet, run the model without randomness, and then check them against common sense, a pocket calculator, a simple Excel workbook. If the modeler has made an error, such as a very common one, mixing up units, minutes instead of hours at a specification, that's going to find it. Then put the randomness back in. If the model uses what computer programmers call an array, something that is subscripted with a subscript or maybe even 2 subscripts, a row and a column subscript, well, the row subscript means first, second, third, or fourth machine on this line. The column subscript is the first column for minimum process time. The second column is for maximum process time. We'd better have that clear, not get them twisted. We'd better document it so that when we come back to the model a few months or years later, my own record in my personal 40 years experience was being asked to revise a model for building a new product at the same factory 11 years after I'd built the model the first time. I was very glad I'd put comments like this into the model. Now, if you have 6 machines, in your mind, they're numbered 1 to 6, the row subscript had better never go 0 or negative, and it had better never get as big as 7. Build in checks. Watch the checks. Did they get up to 6? Why not? Didn't the part ever go to the last machine in the line? All of these are very fruitful ways of checking for common errors that are disastrous when overlooked, but typically routine to fix once you know they're there. Key point, once you realize they're in the model, then you can root them out. And at a more detailed level, here is one of the common ways in terms of coding technique. This is pseudocode. There could be translated into almost any programming language or simulation software, local language. The minute you hear someone begin a sentence with, "Any dad blame fool can plainly see," have your doubts. The code on the left assumes that if it isn't 1, it's equal to 2. The code on the right takes precautions. And the typical precaution that I just labeled abnormal error trap would typically be tell the simulation software, stop the run right this minute, and I'm going to dig into the computer and find out exactly what the heck is going on so that I can check this error. So if nothing can go wrong, make sure to check whether something's going wrong. Now, directional analysis. This means conceptually, the things move in the direction you would expect. If you hypothetically double the arrival rate, and that's a common request among our clients, what would happen if product demand goes up, or the number of patients at our hospital increases as the local population grows? If entities are told to arrive at the model more frequently, queues should either stay the same or get longer. They should not get shorter. If I raise the cycle time of a machine, the utilization percent of that machine should go up if all other things stay the same. And that all other things stay the same is actually a useful hint for how to do this work. Change one thing at a time. Not 3 or 4 things and then watch what's different. One thing at a time, step by step. A 10,000-mile journey begins with one step. And obviously, but it bears mentioning, a simulation clock present in all software, because this is dynamic simulation, that's a major part of its value. Does the clock ever try to go backwards? And I put in a useful analogy here that I learned from a colleague professor of mine at University of Michigan, Dearborn, where I teach part-time statistics. He's a professor of corporate auditing methods. And he mentioned this analogy. Why are we using so much more raw material and yet we're not producing any more product? Maybe the defect rate went way up and we have a huge pile of rejects. Maybe some of that raw material is going home in the trunks of the workers' cars. Similar doubtful mindset is very useful in simulation. And here's some additional things to check. Time units and distance units, consistent. Well, I hope the probe that launched this morning goes better, but a few years back, NASA lost one of its probes to Mars in space because one set of engineers was on yards and another was on meters. Older simulation did not warn about number 2. An entity that had no place to go could simply vanish. Nowadays, to its credit, grid simulation software will say this entity tried to get in the model and it couldn't, so it was destroyed. Are you sure you meant that to happen? Well, probably you did not intend that to happen. Now, previously, I mentioned modular programming techniques. Even though simulation work doesn't usually look much like the traditional hunched over a coding pad or a terminal with C++ or C# or whatever. But have you reused something that was already known to work from your library? And of course, that meant that you and your colleagues, as we do here at PMC, have a library of documented things that are known to work, when they were written, who wrote them, and what specific task they were meant to perform. Here's where you capitalize on those good practices of modular programming. Less chance of error and greater efficiency in use of time, not, as they say, reinventing the wheel. Vitally important, a big simulation model, and I hope it didn't start out big, by the way. I hope it was built up, verified, and validated a little at a time. Every machine in the model, every pathway or route in the model, was it traveled more than 0 times? Was it visited more than 0 times? Did every downtime you scheduled to occur, did it actually occur at least once? Maybe you forgot to schedule it. So if something never got to someplace, check out why. When an error is found within a simulation modeling team of simulation analysts, log it in a logbook. We do. We have a logbook of errors made in the past. Oh, let's have a look here. This doesn't look quite right. Could this be similar to an error somebody else made 5 or 10 or 15 years ago? Our logbook goes back 30 years. We learned this, we might say, from Galileo. He was observing Jupiter and its moons in 1610, and he noted in his observing log that one of the background stars seemed to move. And he wrote, I don't understand why. Maybe I made an observational error. Maybe something is going on I don't understand. 250 years later, astronomers looked at those logbooks. Oh, that was Neptune. We have additional verification of its orbit because Galileo unknowingly cited it. So be thinking of what your ideas are. There's many good ones here, and those of you out there who have already been doing simulation, or very possibly other software development, you have ideas too. Combine these with yours. And now we come to the second half, validation. I already mentioned validation involves the end user much more. Confer early and often. The thing absolutely not to do is, for example, visit the client's facility. We begin by doing that. Now, lately it's been more remote, but we begin by doing that. Learn about the client's concerns. Do a lot of listening while the client describes operation in their emergency department, warehouse, factory, restaurant, hotel registration, airport, whatever it might be, and confer often. Do not tell the client, oh, thank you for this information. I've got it all written down. I'll go back to the office and write a model and call you up in 3 months when it's done. That is absolutely the wrong way to go. Early and often. Here's what we did this week. We typically talk with our clients at least once a week, often 2 or 3 times, on what's going on. Now, and in fact, a previous webinar, and we'll repeat it, looked at issues on input data analysis, some of which are very closely allied to validation. Do we have exactly the data the model wants? And if not, could they reasonably be calculated or estimated? Data having the wrong units. Data bias due to selfish interests. Where I see this problem come up most often is with downtime data. Even before joining PMC in 2002, I worked at Ford 72 to 2001, doing simulation about the last 2/3 of that time. Often when I visited a factory, I would need downtime data on various machines. And downtime data has two parts. How often does the machine break down? And how long does it take to get it repaired? And more than once I was told when I asked for downtime data, get the hell out of here. Pardon my French, not quite that politely. Translated, I'm the shift supervisor here and I do a terrible job of preventive maintenance on my machines, and I sure don't want you to know that. So some digging may be required. If no digging, be a little bit pessimistic. Structured walkthroughs, and they're inherited from good software development practice, are extremely valuable. If I build a small model, I will talk a coworker through it, reproducing out loud the thinking I was doing. And the coworker might say, but how come? And then I might very well say, whoops, well, that's another error that didn't get into production. It was squashed early. And an important concept of a structured walkthrough is, as a bigger model, there might be 3 or 4 colleagues around the desk, and they can, in effect, vote, sort of little paper ballot. Is this model typically one of 4 possibilities? The model is correct. The model has mistakes that can be fixed quickly, and we don't need to meet again to review the corrections. The model has significant mistakes, and after the developer thinks he or she has fixed them, we need to review it again to make sure they're fixed and no new mistakes were introduced. Or number 4, the model is so full of error and so garbled up, the best thing to do with it is throw it away and start over. In a proper structured walkthrough, the winning vote is not the majority vote. It is the most pessimistic vote. After all, remember what happened to Lao Koan. He lived in ancient Troy, and after a long, bitter war, the city inhabitants came out to discover that the Greeks had sailed away, no soldiers in sight, just a big wooden horse. And all but one of them said, at last we have won a great victory. We'll drag this horse into our city and celebrate tonight. Lao Koan was the one lone dissenting voice. I don't trust the Greeks. It may be a trick. Let's not bring the horse into the city, but tonight let's have some soldiers guard it. Lao Koan was banished from the city, and they had a big celebration that night. And you know the rest. So most pessimistic vote wins. And this is one that is particularly valuable in simulation. I'll get some results out of the simulation and present them to the user in the same layout or format as some typical results from the real system, if it's already in operation. What it did yesterday or last week. But I won't label the results. I won't tell the user which is which. I'll ask the user or the client to tell me. And the client might say, well, this one on the left must have come out of your model. How could you tell? Well, the one on the left has no backlog at machine number 4. On our plant floor, we see a horrible backlog there almost all day long. Oh, well, now there's an error in my model, and I have an extremely valuable clue of how to fix it. What's wrong at or near machine number 4? When the client cannot tell them apart, the Turing test has succeeded. And also, it may take several go-arounds, But after a Turing test is passed, your model's going to have a lot more credibility. And the user is going to be a lot more willing to use it to guide business decisions. And that was the goal all along, wasn't it? Statistical analysis. Now, for this, you need at least one statistical competent person on the floor or the project team. That person may or may not be the person who built the model. It doesn't really matter. But the person looking at the statistical analysis of the model output, and that's another webinar we'll be running again, will ask questions like these, considered in detail in that other webinar. These are statistical analyses that either went into the model or are about to come out of the model when we look at the output. Are we looking at the output, even if it's correct output, are we looking at it through a correct, unclouded statistical lens? And here at a level of detail is one quick example on the road to ruin. Even a distribution as basic and common as the exponential has two different forms depending on which textbook you use, which software you use, which reference table you use, and so forth. You'd better know for sure which one is where. If the statistical software is using one, the simulation software is using the other, and you don't allow for it, disaster. The allowance is easy, it's easy to go back and forth, but you'd better be aware of the danger. Now, is the client aware of all the assumptions? And is the client in agreement with them? Well, a good step in that direction is writing the assumptions down and putting them in the project report that the client signs off on. For example, early on in a model building effort, we may assume no downtime. To get maximum possible throughput, what is its limit? The client would need to agree with that and be aware of it. Are we assuming that a particular raw material never runs out, that it's always replenished on time, etc.? Write those assumptions down and go over them with the client. The client should be shown the model animation, and with modern simulation software, the animation effort incremental to build a nice animation is usually no more than 5% of the effort to build the model. So it's well worth doing. So credibility has to be earned. The model should be KISS, keep it simple, only as complex as required. Queuing theory out of a textbook can be used as a partial guide in local parts of the model. You cannot add on validation like putting a hat on a horse. You have to build it in order to earn credibility. So again, be thinking of these ideas in connection with all your own ideas, especially those of you, some of you out there may have done simulation before, others may be coming to it as a new and very promising technology to explore.